Good day, everyone. I am Janus Quiambao, and I am here to present my thesis entitled Molecular Docking Dynamics and Thermodynamic Studies of Theraphosidae Venom Peptides on Human Death Receptors, under the supervision of Dr. Lemmuel L. Tayo. So, for a brief introduction, cancer is one of the most well-studied and well-documented diseases in the world. There are multitudes of mechanisms by which cancer proliferates and cancer grows. Now, what we will want to see here is, can we use venom peptides as a possible cancer therapeutic by it activating a specific receptor within the body that is responsible for the body's natural defense mechanism against these types of rogue cells. Now, here we will be exploring tarantula venom peptides. So why venom? This is because venom is highly specific and selective to protein receptor targets. Why tarantulas? Because tarantulas are widely distributed and popular throughout the world. Now, the mechanism is apoptosis. So why apoptosis? Because apoptosis is a natural defense mechanism in the body. This consists of a receptor, mainly death receptors, that have only been inactivated by cancer. This activation is what we would want to assess in this study. So, what are some potential socioeconomic impacts? So, we have jobs relating to responsible harvesting of venom. Of course, we have patents, and there might be a splinter of this is environmental awareness and ecotourism surrounding these tarantulas. So for the objectives of the study, we are to simulate and characterize the binding preferences of theraphotoxins on different human death receptors, namely the TNFR1, death receptor 4, death receptor 5, and FAST receptor by molecular docking and dynamics. We are to predict the physical or chemical properties and anti-cancer peptide properties and absorption, distribution, metabolism, excretion, and toxicity or ADMET properties. And from here, we are able to quantify the viability of theraphotoxin binding on the death receptors by thermodynamic analysis using binding free energies. So for some scope and delimitations, we are only going to consider human death receptors. Only theraphotoxins with mature peptide sequences that are less than 50 amino acids will be considered. The theraphotoxins are the common name for tarantula venom peptides, and these structures will be predicted and then validated. We're only going to utilize computational simulations, meaning that no wet lab experimentation will be done. Molecular dynamics will only be carried out on the top 3 and bottom 1 of the docked theraphotoxins, and thermodynamic analysis and ADMET will be carried out after molecular dynamics. So for the methodology, here we have a summary of the steps that were carried out in order to do this study. So first is we have the theraphotoxin, Theraphosidae venom peptides or theraphotoxins. We obtain the sequences from a server. We screen for those that are less than 50 amino acids. We load them into anti-CP 2.0. This is a website that will verify its anti-cancer viability. We obtain the top 20 scorers. We obtain the physicochemical properties of these top scorers. We predict the structure via PepFold3, and we verify this 3D structure via mole probability. Now for the death receptors, these are the proteins, and structures are obtained by crystallographic studies. So we obtain the structures from PDB, and we obtain the receptor structure, and then we clean them via autodock. After which we subject the two to molecular docking via HADOC 2.4. We are also going to dock a control, which is the actual death ligand that is going to bind to the death receptor in a biological setting. So after docking, we have molecular dynamics, but we also will be assessing binding favorability and the visualization. For molecular dynamics, we will be doing this via GROMACS, after which we will assess it via a simulation analysis and visualization, after which we are going to assess the thermodynamics of binding via GMX MMPBSA, and finally we are going to assess the ADMET evaluation via ADMET Lab. So for the results and discussion, First is we go to the anti-cancer peptides as a result of the screening. Now the top peptides here come from spiders native to China with the exception of G. rosea and H. gigas. Now what we really want to see here are the physicochemical properties. The slight hydrophobicity and medium ambipaticity indicate that these are good anti-cancer peptides. Low hydrophobicity means that it may be difficult in permeating through the bilayer, but since that receptors are extracellular, this is not a problem, such as the problem with steric hindrance and side bulk. Charges being ranged from -2 to 5 to +3 indicates that some of the peptides may be ideal as anti-cancer because ideal is cationic, while some are non-ideal because they are anionic. Now we move on to the molecular docking. For HADOC 2.4, the general rule of thumb is the more negative the HADOC score is, the more favorable is the binding. For the det receptor 4 system, we have top peptides D, E, B, the lowest being Q. The score of the top peptide D is magnitudes less favorable than that of the actual det ligand, which has a value of -152.1. For det receptor 5, the best scoring peptides are Q, H, and O. The lowest is P. The score of Q is comparable to that of that ligand because of their similar HADOC scores. For TNFR1, the top peptides are A, B, and M. The lowest is C. The score for A is better than that of the actual det ligand, which is at around -40, with A being at around -243. While for Fas, the top peptides are O, N, and I, and the lowest is M. Again, similar to the det receptor 5 system, we have similar binding HADOC scores as compared to the det ligand. Now here we have the 3D configurations of the docking. So for det receptor 4, this is the det receptor 4 system, we have predominantly slanting, almost horizontal docking, where the det receptors encircle the peptide in a slanted or horizontal manner. For det receptor 5, we have clasping, but it's much more vertical than the det receptor 4 system. For TNFR, this is the ideally what we find in crystallographic studies of the actual binding of det receptors to det ligands, where we have vertical clasping. And for Fas, we have a mix of slanted and vertical. So now we go to the molecular dynamics simulation. So let me play here these systems. Now, as you can see, you may find some systems weird, such as that of Trail, the actual det ligand, and Jingzhou toxin 41, where you may see some jumps. Now, the simulation may look weird, but these jumps are an effect of the periodic boundary conditions. These are implemented to mimic an infinite bulk environment where the box is replicated in all directions to simulate continuity. What really happens here is that when the protein goes beyond the edge, instead of simulating a second box, GROMACS wraps the protein onto the other side, thereby the jumps, ensuring that the interactions between atoms are calculated as if they were in a continuous, infinitely repeating environment. Now, the jumps do not undermine the underlying physics and chemistry of the simulation, and it does not really negatively affect the calculations done in the system. What we are also interested in the molecular dynamics simulation are these graphs of the RMSD, or the root mean square deviation, which is a measure of the deviations being done to the system from the initial dock configuration, the RMSF, which identifies which parts of the atoms are flexible, the SASA, or the solvent accessible surface area, which calculates the area that are free to be intruded by solvent molecules, i.e. water, and RG, which is a compactness, which is a measure of the compactness of the overall system. We have hydrogen bonds and hydrogen bond distribution, and the minimum distance within the system. What we want to assess here is the closeness of these peptides to the actual trail. So for RMSD, we have here very much similar profile to trail. RMSF, of course, there's going to be differences because the composition of the theraphotoxins and the death ligand are different. For radius of gyration, we expect that trail will have a larger value because it is larger and therefore much more flexible. And this is a consequence of the high value of the SASA, because the larger the system, the more surface area is possible for solvent molecules to intrude. We have here the hydrogen bonds. Of course, larger system will have more hydrogen bonds. Hydrogen bond distribution, it narrows out to around 0.29, and the minimum distance, we see that there are no differences. So what we see here is that generally the death receptor, death ligand, and death receptor theraphotoxin system have very much similar profiles, which is what we are looking for. Now we have here also for the death receptor 5, and again for the molecular dynamics we have similar profiles as we see in the death receptor 4 system. Again, this is a good indication. Then we have for TNFR1, much more stable, no, not much jumping. Now we go to the graphs. We may see some outlier here, but generally we still find the same profile as we see in the DR4, DR5 systems, which is good. And finally for the FAS, and here are the graphs for the FAS. Again, we see very similar profiles. There may be some deviations, but these deviations are not that significant to merit some form of disagreement within the profiles of the death receptor, death ligand, and death receptor theraphotoxin. So bottom line is the similarities of these profiles are good because this is what we want to see in the molecular dynamics simulation. Now we go to the thermodynamics. We have here the results from MMGBSA. We have delta G of binding that are mostly positive because MMGBSA is an implicit solvation model that does not consider solvation effects. However, when we consider solvation, such as here in MMPBSA, we have mostly negative delta G values, which is favorable. So MMPBSA is much more accurate because it considers electrostatics and ionics, and majority of these are negative, which is again a good indication within the system. Finally, we have the ADMET analysis. High PPAP indicates good intestine permeation. Low HIA, on the other hand, means bad intestine absorption. Low BBB means that it cannot pass easily through the blood-brain barrier. Inhibitors and substrates of CYP 450 indicates that careful consideration must be done when taking this therapeutic in conjunction with other therapeutics. Low half-time life means that it is easily excreted through the body. Low HHT means that it's very much non-hepatotoxic. Low Ames means that it is unlikely to induce genetic mutations. High hERG means that it may possibly be pro-arrhythmic. And high LD50 means that it is low in toxicity. So we go to the conclusion. From this study, we have found that the theraphotoxins have mild anti-cancer viability and have some ideal anti-cancer properties. They mostly bind favorably to death receptors. They are stable when left bound to death receptors as compared to the binding of death ligands. We have shown that they have favorable thermodynamic binding, but it's not as negative as the actual death ligands. And they also exhibit favorable ADMET properties, with the exception of HIA, CYP, and hERG. So for the recommendations, future studies may focus on experimental validation of the results, given that this is a computational study. Also, we may test against known recombinant proteins or other apoptosis-inducing therapeutics and test on other protein receptors associated with cancer. And we may also shift to improving current ADMET properties of these peptides, finding out the optimal dosage, and determine other possible therapeutic potentials for these theraphotoxins. That is it for my presentation. Thank you and have a nice day.